Hello everyone, this is Anuttam Anand, registration number 19 BCE 1285, and the topic of my presentation is Elgamal Cryptosystem. Let's first talk about Elgamal encryption. So what is Elgamal encryption? So it is a public key crypto system. So it uses asymmetric key encryption for communicating between two parties and encrypting the message. So what does this mean is that it uses asymmetric key encryption. So in asymmetric key encryption, we have two keys. One is for encryption, and the message is sent to the second party. And at that point, the party uses another key to decrypt the message. So that is the scenario which we use for communicating between the two parties involved and also encrypt the message. So this crypto system is based on the difficulty of finding discrete logarithm in a cyclic group. That is, even if we know Ga and Gk, it is extremely difficult to compute g to the power ak. So what does this mean is that in this crypto system, uh, the the encryption is based on the difficulty of finding discrete logarithm within a cyclic group. So even if we are given a Ga and Gk, it is infeasible to find g to the power ak. So now let's talk about what is Elgamal crypto system. So it was presented in 1984 by Arthur Elgamal, and the main features or the key aspects of this crypto system were: first thing, it was based on discrete logarithm problem. Second, it was randomized encryption application. Third, it it established a secure channel for key sharing. And fourth was it was used to encrypt messages. So now we will talk about the idea of Elgamal crypto system. So we will take a scenario in which Alice wants to communicate with Bob, and how the two parties do the encryption and how the messages pass to one another. So let's first jump into the scenario. So the first scenario is that Bob generates public and private keys. So in this one, what will happen is that Bob will generate a pair of keys. So how that will happen is, first Bob will choose a very large number Q and a cyclic group FQ. So from that cyclic group FQ, he will choose any element G and an element A such that GCD, that is the greatest common divisor of A and Q, is 1. Then he will compute H, so H will be equals to GA, and Bob publishes if H equals GA, Q and G as his public key and retain A as his private key. So after this first scenario, what will happen is Bob has generated some set of values. So these set involve F, H, Q, and G, and all these four are public. Public means that anyone from anywhere can know that okay, these are the elements which Bob generated, and he or she can use that. While A, A is still kept as private key. So what is private key? That is, it is only with Bob, and only Bob has knowledge of this private key. So now let's jump into the second scenario. So now Alice wants to send a message to Bob, and she will encrypt that data using Bob's public key. So what will happen in this is Alice selects an element K from cyclic group F such that GCD of K, comma Q is 1. So again the greatest common divisor for K, which was selected from the cyclic group F, and Q. So Q is again from Bob's public elements. So the GCD of K and Q is 1. So now we have got our element K. So after this, she will compute P equals GK and S equals HK, which is also equals to GAK. So now if we go back, we don't have any P which Bob generated. So we are generating this P. So we are using G and K. So we have G as Bob's public key. So we can use that. And then in the second one, we have S equals to HK. So again, H is public. So Alice can use Bob's H element, and she can multiply it with K. So since we know that H was equals to GA, so S will be equals to HK, which is also equals to GAK. So now she will multiply S with M. So what is M here? M is the message that Alice wants to send to Bob, but in an encrypted manner. So then she will multiply whole message with S, and then she will send P comma M multiplied by S, and which will be equal to, so since we can see that P equals to GK as here, and M multiplied by S equals to M multiplied by S. So she will send this information to Bob. So now coming to the third scenario, that is Bob decrypts the message. So now the message has traveled from Alice's side and it has reached Bob. So now what will happen at Bob's end is Bob will first calculate S dash. So S dash will be equals to PA, which is equals to GAK. So now why we are using A is because A was the private key of Bob. So now Bob can use A and he will calculate S dash. So which is equals to PA, which will also equals to GAK. So G we know, A we know, and K also we know at Bob's end. So now he will divide M multiplied by S dash to obtain M because S equals to S dash. So now he can obtain the original message M from the message which was sent by Alice. So if you think about it, if anyone else got the same encrypted message from Alice, so they won't be able to obtain the original message because they don't have A. So A is required to calculate S dash, and which is S dash is required to obtain our M, which was the original message sent by Alice. So now this is the pictorial representation of the scenario which we talked about. So this is Alice and this is Bob. So Alice has a plain text P. So let's say she sends a message, hello, how are you? So that plain text message will go under some computations. So you can see E1 to the power R mod P, and then C1 is again calculated as E2 to the power R multiplied by P mod P. So that's how it's encrypted, and it will be converted to a ciphertext, and this will be again go here. So P equals to C2 multiplied by C1 to the power minus 1 mod P. So after this, we will decrypt it using Bob's private key, and we will get the plain text. So we can see the elements E1, E2, and P. These are coming from Bob's head, which are from his public key, E1, E2, P. And we can see here that how Bob generated his key. So he selected P, which is a very large prime number, and he selected E1, which is primitive root, and then he selected D. So E2 was equal to E1 to the power D mod P, and then he got this private key D, and using this private key D, he was able to get the plain text from the ciphertext. So now coming to the four parts of Elgamal Cryptosystem in a brief manner. So the first part is key generation. So how this key generation happens. Now we will talk about it. So the participant A generates the public private key pair. So there are two participants, A and let's say B. So the A will generate a key pair that is public and private. So how that happens is A will generate large prime number P and generator G or the multiplicative group Z multiplied by P of the integer modulo P. So after this, he will select an integer A such that A lies between 1 and P minus 2. So P came from this, that is a large prime number. So A lies between any number between 1 and P minus 2. And after this, he will compute GA mod P. So in the third step of key generation, A's public key. Now after all these computations, A's public key will contain P, G, and GA, and A's private key will contain A. So this is all similar things which we talked about related to Bob. So now coming to the second procedure, that is the encryption procedure. So participant B encrypts a message M to A, obtain A's authentic public key. So now in the last step we saw that we have P, G, and GA as the public key of A. So using those three elements, we will obtain A's authentic public key, which will contain the element P, G, and GA. So now we will represent the message as integers M in the range 0 to P minus 1. So in the third step, we will select a random integer k such that k lies between 1 and p minus 2. And in the fourth step, we will have gamma equals to gk mod p and delta equals to m multiplied by GAK. So in the fifth and the last step of encryption procedure, we will send a ciphertext C, which will be equal to gamma, comma, delta, and that ciphertext text will be sent to A. So that's how our encryption procedure will happen. And this is same what Alice did, and she sent the encrypted message to Bob. So now coming to the third part, which is the decryption procedure. So what happens in decryption procedure? So everything happens on A side, who was the owner of the public and private key. So what will happen is A will receive the encrypted message M from B. So B has sent this encrypted message to A. So A has received it. But the message is still encrypted and not in human readable form. So now what will happen is using the private key A, we will compute gamma P minus P to 1 to A mod P. Sorry, gamma P minus 1 minus A mod P. But note here that gamma multiplied by P minus 1 minus A is also equals to gamma minus A, which is also equals to A minus A multiplied by K. So using this formula, we will recover M, which was the original message, by computing gamma minus A multiplied by delta mod P. So now we can see that when Alice sent the ciphertext to A, so she was sending gamma and delta to A. So we have gamma and delta here. So A was already known on the participant A side, which was the private key, and P was the big primary number, which was generated by party B. So that's how the Elgamal cryptosystem works. So we talked about three procedures: key generation, encryption procedure, and decryption procedure. So now let's take a quick example using numbers. So let's say we are on the encryption sample. So Alice chooses her public key, let's say 17, 6, and 7, where P equals 17, generator G is 6, and private key part A is 5. So the public key part GA mod P will be equal to 65 mod 17, which is equals to 7. So we can see that public key contains 7, 6, and 17, and the private key is 5. So Bob encrypts the message M equals 13. So he chooses a random K equals 10, calculates the gamma here, which is 610 mod 17, which will give you 15. And then he encrypts the delta, which will give 9. So Bob sends this delta equals 15, sorry, gamma equals 15 and delta equals 9 to Alice. So on Alice's side, the decryption sample will happen. So what will happen is Alice will receive the gamma equals 15 and delta equals 9 from Bob. So her public key is PG, GA, which is 17, 6, and 7, and her private key is 5. So Alice now decrypts the message using her private key. So what happens is she will have a decryption factor, that is del gamma minus A multiplied by delta mod P, so which will compute to 9. So the decryption delta multiplied by 9 mod P will give 13, and Alice has now decrypted the message and received 13. So you can see that original message sent by Bob was 13, and after computing everything, we have received the original message 13. So now let's talk about summary of Elgamal cryptosystem. So first one, the features. So the features of Elgamal cryptosystem are use of a random factor k for encryption. So since we are choosing a random factor k, so it is very hard to guess this number, and it is a very foolproof plan. So second is variant of DH shared secret is a GAK. So the problem with Elgamal cryptosystem is it duplicates the message length. So the message which was sent, so it has a duplicated length, and it depends on interactability of DL and DH. So there's one more algorithm, RSA, which is again an asymmetric algorithm, and it is very popular. So now we will compare RSA and LML. So first, what is an asymmetric algorithm? So it is just an encryption technique that uses different keys on the process of encryption and decryption. Because classically, we used to have only single key in the symmetric method, and we used to encrypt and decrypt using the same key, and that key should be with the sender and the receiver. But that was a very insecure way. So now the asymmetric algorithm was created, which uses different keys of encryption. So let's say P1 is used for encryption and P2 was used for decryption. So the sender will have P1 and the receiver will have P2. So this algorithm uses two keys, public and private key. So the public key is publicly distributed, while the private key is kept confidentially by the user, and this key is required at the time of decryption process. So RSA and Elgamal are two algorithms that implement a public key crypto system. So the strength of this algorithm lies in the bit length use. So in the asymmetric algorithm, the strength of the algorithm lies in the bit length use. So like how long is the length of the bits? So the degree of difficulty in RSA lies in the factorization of large primes, while in Elgamal it lies in the calculation of discrete logarithms. So since we talked initially that Elgamal is based on discrete logarithms, but RSA is based on factorization of large primes. So after testing, it is proven that RSA performs a faster encryption process than Elgamal. However, Elgamal decryption process is faster than RSA. So what does this mean is that performing the encryption process, so RSA is faster, but in the whole decryption process, Elgamal is faster. So both of these algorithms are cryptographic public key algorithms, but have functions in different ways. So whereas RSA is a deterministic algorithm, Elgamal is a probabilistic algorithm. So this is a chart and a table. So as we can see, RSA and Elgamal, so it was RSA was generated in 1977, whereas Elgamal was generated in 1984. So performance-wise, RSA is fast and Elgamal is also fast. So since we saw that RSA's encryption is fast, whereas Elgamal's decryption process is fast. So now coming to power consumption. So RSA uses higher power than Elgamal and security attacks. So RSA only has one single attack, which is timing, but Elgamal has adaptive chosen cipher text attacks. So in the hardware and software implementation, RSA is not very efficient to implement, whereas Elgamal is very efficient and fast. So if we talk about the security strength of both the algorithms, RSA depends on factoring the product of two large prime numbers, whereas Elgamal depends on the computing of logarithms. So even if we see this chart, we have RSA, Elgamal, and Weiler. So as the file size increases, the time taken to process the encryption in RSA LGML varies. So we can see in the red line, which is LGML. So first it increases, then it drastically comes down, and then it increases again as the file size increases, but then again it comes down. Whereas in RSA, it first increases, goes, sorry, whereas in RSA, it increases, then also increases, and it keeps on increasing as the file size increases. So we can say that LGML is somewhat a good algorithm as compared to RSA in a few of the concepts, and it can be used in the blockchain purpose. And yeah, so thank you.